In this video, you will learn how to analyze, compare, and stack products using NEEP's cold climate air source heat pump sizing tool.
For more information on cold climate air source heat pump sizing and specification, check out these related NEEP resources. Here are some other videos related to the NEEP cold climate air source heat pump tool and sizing an air source heat pump.
In this video, you will learn how to analyze the heat pump visualization tool, compare multiple heat pumps, and build and analyze a multiple compressor or stacked heat pump system. For guidance on how to navigate the tool, refer to the key features video. In order to properly analyze the system, we must complete an advanced search. For the purposes of this video, I will continue using the same search as in the key features video. Here I have entered all my information, including the desired brand and ducting configuration, as well as the information for the heating design load and cooling design load, and zip code and nearest weather station. For your project, enter information specific to what you are looking for, as well as the calculated heating and cooling design loads and the heating and cooling design temperatures.
It is recommended to use industry-approved practices like ACA's Manual J to calculate the heating and cooling design loads, and ACA's Manual S to size and select equipment. The third edition of ACA's Manual S allows for sizing for heating.
Use the proper zip code and nearest weather station to generate the most accurate visualization for your home. Now that we've conducted our search, I'm going to scroll down in list view and analyze the systems. To do this, I'm going to sort by present design load served to get the highest percentage at the top and the lowest at the bottom. You could see that percentages over 120% are yellow, percentages over 150% are orange, and those over 200% are red. This colorization is to discourage oversizing and alert the user that the heat pump selected may be oversized for the entered loads. I'm going to select this piece of equipment that is 206.5% design load served, has 100% annual load served, and percent annual load modulation is 37.5%. Our initial thought is that a heat pump that puts out 23,745 BTU per hour at the design temperature would be a good fit for a heating design load of 11,500. It should keep the place warm. However, let's look further. As we open up the product page for this selected product, we should scroll down to the system capacity, heating and cooling load, and weather data graph. In this graph, we can analyze the visualization of how the system should operate year-round. Currently, we are looking at the heating season operation. You can see in the background the annual load times hours histogram, which peaks around 36 degrees, which means most BTUs per year is around this temperature. Further left is our design temperature, which is 14 degrees. At this spot, you can see that the load line is well within the modulating zone, which is the area between the heating maximum capacity and the heating minimum capacity. Within the modulating zone, the variable speed heat pump will modulate its output to meet the needs of the space it is heating or cooling. This is typically where a heat pump will operate most efficiently and keep the space most comfortable. For this specific piece of equipment, we can see that the heating maximum capacity stays above the load line for temperatures well below zero. If we scroll down to the product sizing for heating page, we can see that the capacity balance point, or when that heating maximum capacity line crosses the load line, is at -8 degrees. For the selected location, we can see that -8 degrees is a very rare temperature and does not happen in a typical year. We can see that there are 0 hours throughout the year requiring supplemental heat for this selected heat pump. If we analyze the graph further, we can look at this red wedge on the bottom right, which is the potential low-load cycling zone. The potential low-load cycling zone is when the heating minimum capacity is above the heating load line. You can tell that the heating load line, after it crosses the heating minimum capacity line, turns from this green color to this orange color. In this potential low-load cycling zone, the heat pump may cycle on and off, which causes inefficiencies and could decrease comfort. We can see that the potential low-load cycling zone encapsulates the temperatures that the annual load times hours peaks. A heat pump that will operate effectively for most annual load hours should be within its modulating zone for most of the annual load times hours. To analyze the system further, let's add in cooling. If we look at the cooling, we can see that the cooling low load cycling zone encapsulates almost all of the cooling annual load times hours. This means that for a majority of the cooling season, this heat pump may cycle on and off. A heat pump or air conditioner with short run times may not dehumidify as well as a piece of equipment with longer run times. It is important to analyze both heating and cooling minimum capacities as well as the latent capacity removal of this heat pump. Use approved methods like ACA Manual S to size a piece of equipment. This oversize warning will pop up for pieces of equipment that are over 120% of the heating design load served. Now that we have assessed an oversized piece of equipment, let's look at a piece of equipment that may not cover all of the percent design load served. I'm going to select this heat pump with 73% design load served that has 87.8% annual load served and 72.7% annual load modulating. As we scroll down to the system capacity, heating and cooling load, and weather data graph, we can analyze this undersized system and how it should operate year-round. We can see that the potential low load cycling zone is now green and relatively small and does not cover the peak of the annual load times hours. It only goes to 47 degrees at the minimum capacity threshold. However, we can see that this undersized piece of equipment now has this purple wedge in the top left. This purple wedge is the supplemental heat needed to meet the load of the space in addition to what the e-pump is able to output at each given temperature. If we analyze the product sizing for heating, we can look at the capacity balance point of 23 degrees Fahrenheit as where this heating maximum capacity crosses the heating load line. Below this temperature, the heat pump may need supplemental heating to meet the load of the home. We can look at the hours requiring supplemental heat to see how many hours annually will need supplemental heating engaged. This number is 340, or 6.2% of the entire year. It is important to remember that these hours requiring supplemental heat are unlikely to be consecutive and are most likely sporadic throughout the colder nights of the year. The internal temperature of the home may not drift much more than a degree or two throughout these hours requiring supplemental heat if supplemental heat is not engaged. However, it is important to use this tool to visualize the amount of supplemental heat needed. If we add in cooling to the graph, we will see that this smaller piece of equipment will likely operate better throughout most of the cooling season. This smaller piece of equipment handles the cooling load better than the previous piece of equipment because the cooling minimum capacity is lower than the previous. However, you can see that the cooling low load cycling still encapsulates a majority of the annual cooling load times hours. It is not uncommon for a heat pump that is sized for the heating design load to be oversized for the cooling design load. In scenarios like this, where the heating design load is almost twice the cooling design load. This is why it is crucial to complete industry-approved sizing and selection processes like ACA Manual S. Now that we've looked at a large piece of equipment and a smaller piece of equipment, let's look at a piece of equipment that is around 100% design load served. I'm going to look at this heat pump that is 107.7% design load served, 97.9% annual load served, and 80% annual load modulating. As we scroll to the system capacity, heating and cooling load, and weather data graph, we can visualize how this piece of equipment will operate year-round. We can see that there is a wedge in the top left for the supplemental heat needed. However, that capacity balance point is 11 degrees, which is below my heating design temperature. Therefore, supplemental heat will likely not be needed. There is also a potential low load cycling zone, but that potential low load cycling zone is small, green, and does not encapsulate a majority of the annual load times hours. Looking at the heating load line, we see it is green for a majority of the annual load times hours, and therefore within the heat pump's modulating zone. If we scroll down to analyze the product sizing for heating section, we can see the capacity balance point is below our design temperature of 14 degrees. The minimum capacity threshold is 46 degrees, which is relatively good. And this piece of equipment only requires supplemental heating for 42 hours per year. Again, these 42 hours are likely not consecutive and are sporadic throughout the coldest nights of the year. The internal temperature of the home is unlikely to drop more than a degree or two if the heat pump is still outputting its maximum capacity. Now let's add in cooling. We can see that the selected piece of equipment has a relatively small cooling low load cycling zone. The cooling minimum capacity crosses the cooling load line at the minimum capacity threshold of 82 degrees Fahrenheit, relative to our oversized piece of equipment, which crossed the minimum capacity threshold at 89 degrees Fahrenheit. That means this heat pump will modulate for more hours than the larger piece of equipment. In summary, we can tell that this heat pump is right sized for the entered loads because it has small supplemental heat zone that is below the design temperature, and it has small potential load cycling zone that is 46 degrees and above, which is relatively good, and it has a relatively small cooling low load cycling zone as well. So this heat pump should operate effectively year round. Now that we've looked at all three individually, let's select and compare the three heat pumps we just looked at using the comparison tool. To select heat pumps to compare or stack, click the plus sign on the left side of the screen. Multiple counts of one type of heat pump can be added. However, this removes the Compare Products feature from the tab. To reduce the count to 1 and use the Compare Products, simply click the minus button for each piece of equipment that has more than one count. Now that the Compare Products is back, let's view. In the Compare Products stage, we can look at our selected pieces of equipment. Comparing the system capacity, heating load, and weather data graphs for each piece of equipment, we can visualize how well each piece of equipment should operate year-round. We can see that this graph is likely the oversized piece of equipment because it does not need supplemental heating as the heating maximum capacity is well above the load line at the design temperature, and it has a large potential low load cycling zone. We can see that this graph is likely the undersized piece of equipment as it has a large supplemental heating zone and needs supplemental heating at the design temperature. However, it has a small potential low load cycling zone. If we scroll to our third piece of equipment, we can see that it does not need supplemental heat at the design temperature, and it has a relatively small potential low load cycling zone. This is likely the right size piece of equipment when comparing these three. We can use this AHRI number to match the piece of equipment below. This AHRI number ends in 099, which matches the piece of equipment on the right. If we scroll down to analyze further, we can compare efficiencies, Energy Star certification and tax credit eligibility, as well as product sizing for heating information. To build a multiple compressor system, go about the selection as we did previous. For this multiple compressor system, I'm going to add two of the undersized pieces of equipment we previously looked at. Then I will click Stack Products. This multi-system capacity, heating load, and weather data graph shows no supplemental heat needed for annual operation and has a very small single system low load cycling zone. This system has a total maximum capacity that is a sum of both compressors working together at its maximum capacities. This system also has a single system minimum capacity. This single system minimum capacity represents one heat pump being turned off while the other heat pump is operating at its minimum capacity. If we look at the total system minimum capacity, this is each heat pump operating at their minimum output. The modulating single system zone is the zone between the total system minimum capacity and the single system minimum capacity. We can see that this multiple compressor stack system can operate annually without any supplemental heating and has a relatively high minimum capacity threshold of 47 degrees Fahrenheit. This two compressor system meets the entered loads very well, should provide efficient comfort, and does not require any supplemental heating. Once again, this should all be confirmed by approved sizing and selection methods like ACA Manual J and ACA Manual S. Thank you for watching. To use the cold climate air source heat pump sizing tool, visit ashp.neep.org. For additional guidance, visit our ASHP installer and consumer resources page at neep.org.